Hi again. In my last video I built the design and run it with the software for bare metal just for checking, and then we build the Linux operating system with the interrupt. We did everything as we used to do, but we had two stages. One was enabling the user space IO platform, and the second is to add a file systemuser.dtsti to define the interrupts and to work them. In this video we will load the Linux from the Vitis XSCT console. Here we have a few stages. I added two more. First we need to connect to our board, then we need to set the target, then we need to download the FSBL to configure the DDR, and we'll let it run. Then we'll stop it and we'll load the U-boot, and then we'll let it run. Then we'll see some messages on the UART. Then we'll download the image to the address that the U-boot expects the kernel to be, and then we give a command to the U-boot by the term, the UART, and we'll see the Linux running. And next we will see the two files needed to set the application for the interrupts, and then we'll check the prog interrupts file, and we'll see it working manually. So we arm each interrupt, we generate the interrupt using the push button, and then we check the interrupt, checking this file again, and we'll see that the interrupt fired. Then we will write the application. In the application we have a new subject here. We have a special thread. We'll know how to define a thread, so we'll have a multi-thread application. We'll write the handles for the interrupt, and we will count in the main application just to see it running. As usual, I give all my files in my GitHub. I will open a branch Linux in my interrupts repository, and that's it. Let's get to work. So we're done with the Linux, and we have all the files in our shared directory under Linux. I'll insert a newly formatted SD card to my SD card slot, and I'll turn on my board, keeping the switch in the JTAG position because we want to load the Linux into the DDR and not load it from my SD card. Now we'll go to our Vitis, we'll go to our Vitis and we'll use our XSCT console. We can address it from here even without a project. I'm using the old bare metal project. We'll cd to our shared directory, our Linux directory. I'll reverse the backslashes, and we'll dir. Now the first thing we want to do is to connect to our board. The command is connect. Then we check the targets, and we see here the two cores of the ARM, the zinc and the PL. We'll target the first core, and here is our target. Now we'll load the FPGA. The command is FPGA -file and the bit stream. This is the bit stream from our XSA. It's loading and our LED is on. Next, we need to configure the DDR controller. For this we need the FSBL. So we download the Zinc FSBL.elf. This is a software, so it knows where to go. And we run it by giving the command continue. Now we need to load the U-boot. For this we need to stop the FSBL and load the U-boot. DOW, again it's a software, and we load it and we'll run it again. Now we will have messages from the U-boot here. And we can see here in our term that the U-boot tried to find the kernel in this address, but since we didn't load it yet, it's not there. So this is the address we need for the kernel. So again here, we'll download the kernel into the DDR, but this is not a software, it's a UA. So we use -data, the image, and we need to give it an address, and we'll take the address from here. And we'll download it. And since our U-boot is up, we'll give the command to bootman from this address. And here we have our Linux. We can pwd, we can ifconfig, and we have a config. And we can look at our SD card. And it's empty. Now, as before, we had here the boot.bin, the boot SCR, and the image on our SD card. So this is what we want to do. But since we have a Linux on and we have the IP, we can do this by Command Pro. So we open Command Pro in our Linux folder. So SCP, we need to copy it, boot.bin, here to the SD card, to root, at the IP, and the directory. And oops, something is doing something nasty. As you saw here, the Linux generates an RSA key. My computer is familiar with this IP and another from previous Linux that I used. So we go to this file, this folder, C user owner, and here we have known addresses, and we can see the old RSA key. Now we don't really need it, so we'll delete this file, and my computer will generate a new file for this system. Now we'll do it again. Everything is okay. Yes. As you know, username is root and password is also root. And here we have the boot.bin. The same goes for SCP boot SCR, root, and the same goes for the image. And here are my 3 files in the SD card. Now we can disconnect our board, switch from the JTAG to the SD card, and we'll boot this time from the SD card. And we have the Linux is up again. I have config, the same, everything as we're familiar with. Now the next thing is to check our interrupts. First, we need to check that we have the files for the interrupts. The files are at dev UI something, and we have the dev UI 0 and the dev UI 1. For every interrupt we have a file that we need to control while running the application, and we have a new file for the interrupt itself. So it's in prog interrupts, and here we see all the system interrupt for this Linux, and here we have the 2 interrupts for the push buttons, btn0 IRQ and btn1 IRQ. Next, we want to check manually that the IRQ are working. So first we need to arm them. We press echo into those files that we saw earlier, dev UI 0 and dev UI 1. So now they're armed and ready to go, and we can press the 0 interrupt and check the interrupt file, and here it is, it was fired. Next we can press the second interrupt, and again 1 for the second interrupt. Now we press again the first interrupt, number 0, and nothing happened because we need to rearm the interrupts. So we rearm 0, we rearm 1, and we check the interrupt. Now the second interrupt appear because it was waiting in the belly. So now we can press again on the 0 interrupt, on the 1 interrupt, and on the 0 interrupt, and we need to clear them. And here they are. So our interrupts are working, and now we want to write the application, the Linux application. For the Linux application, we need a new directory here. So I'll open a new directory, a new folder. I'll call it int Linux application, and I'll export the hardware again. I can copy it, but I'll export it to this newly created folder. Here. And here it is. Now let's launch Vitis. We'll direct it to here. And now we can start with our Linux application. We'll create application project. We'll use our XSA. We'll call this int Linux application, and we'll address it to SMP with the Linux, and we'll start an empty application. Before we begin, we need to make some changes because we want to use threads. To use threads, we need to go to our project, go to Properties, go to C build and Setting, and here we need the linker, here in the miscellaneous, and we need to add a library for the threads. This is called -lp thread. This will enable us to use a multi-thread in our application, and we need one thread to check for the interrupts. Now we apply and close, and now we will create a new file for our project, int Linux application.c, and we can start writing. First, we need the includes. As you can see here, we have thread.h and poll.h. Poll will be used for pulling the interrupts. Actually, the thread will be asleep until the interrupts occur. When the interrupts occur, the kernel will wake up the thread, deal with the interrupt, and go back to sleep. We'll talk about it in a minute. We'll start the main. And we'll close the main. Now we can start writing. The first thing we need, since we have two interrupts and we want to establish them, we need a struct for two interrupts. So we'll define a struct, we'll call it IRQ data, and we'll call for it here in the main. So we will have the data for the struct. Here is just two ints, one int for reading the first file and one for the second file. So that's what we're gonna do. First, we'll write fd0, we'll open the dev UIO0 for read and write and put the int here in the struct, and the same for the second struct. And if anyone is under 0, which we don't means it doesn't have this file in the Linux, this will produce an error, but we saw that we have them, so we're okay. Now, like I showed you in the manual operation of the interrupt, we need to arm the interrupts. In the pool.h we have the write function. We just need the int from our file and enable it with 32 bits of 1 and the size of it, and here we arm. This is the echo 1 into this file. This is how we do it in the application. Now we want to generate a thread, so we'll declare a thread, and we need to declare the thread. Now the thread, we'll open it, will be declared here. This is compared to controlling the interrupt controller in our bare metal function. First, we need again the struct for the two interrupts for the data here, and this is what we get for our thread. We need to define two variables for the interrupt. We need them both, so we have an array. So we generate an array with the pool fd struct that is declaring the pool.h, which have an fd field and an event field and some other field which we don't need now. And this is where we store all the interrupt data. Now we'll have a while loop. And close it. And in it, we'll check if there is a poll. A poll is a function, again, in a poll.h that checks this array. This is why we need it as an array, so we'll have only one parameter here and we have two interrupts. And this one checks if either one fired. If it does, it wake up the thread and deal with it, and then it go back to sleep. Now we check if either one was fired, and then we need to know which one. So if it was the first one, from here, if it was pulled, we will go to its handler, which will be here in the state. If it was the second one, we'll have a different handler. So this is our thread, and we still need the handlers, the two handlers. Now in the handler, which are actually function at this stage, since we got the interrupt ID, we need to read it into IRQ count. then we'll deal with it, and then we will need to rearm the interrupt. So what we want to do in this interrupt, we want to count how many interrupts were fired. For this we need two counters here, one for interrupt 0 and one for interrupt 1, and once we fire interrupt 0 counter will rise and we'll get a print and we'll close. And the same goes for the second interrupt. So now we have two handlers in a thread, which we define here the thread, and we need to create it. Here we create the thread variable and the thread function, and we transfer the data from here so we get the two interrupts. It's a struct with the two interrupts. So we declare the thread, and it's actually sleeping all the time until the interrupt will be fired, and then it will wake up, handle it, and go back to sleep. So the next thing we want to do is to zero the counters and wait for an interrupt. By the way, if we open those files, we of course need to close them. Now what we want to do while we wait? In the previous we just waited for anything. For here I want to show you that the computer is still working. So I'll let it sleep for 1 second. Then I want a counter to count the time. So I'll add a counter here, a time counter. I'll zero it with the other counters. Here, and I'll increase it for every second. And after increasing it, we'll print a message that we counted as many seconds as we counted. So we actually can see that the application is still working and the interrupt will interrupt it. So this is our software, our application. We have the main, which runs, which configure the thread. We have the thread with its handler, and we keep counting until an interrupt will interrupt us and we'll see it running. So now let's save this, compile this, and we're ready to go for the board. Here is again my Teraterm, and let's debug. We go to debug, debug configuration, single application debug. We need to connect to our board. So we'll add a new Linux agent with the IP as name and host, and we test the connection. Successful. We see here that we go to the SD card as usual. And let's debug And we're ready. Here is our software in the SD card. And let's start running. First, we'll start. Then we define the two interrupts. It's okay, so we move on. We arm the interrupts, and now we generate the thread. Zero everything, and we wait for the interrupt, so we start counting. And here our application is counting, and we can press the first interrupt and we got a message, and we can press the second interrupt and we got a message, and again the first, and again the second, and again the second, and our application is working. Now here, if we want to look at the interrupts, we see that we have 5. Before we had 3 and 2, and now we generated 2 and 3, so now it's 5 and 5. And if we press again, we'll get another message on the 0, and the 0 will be 6. And we press again, we'll have the same. So this is how we use interrupt in user space mode in Linux. I will have all my file as usual in my GitHub. I'll have a branch Linux, which I'll add the application. I will also add a script to how to load Linux to the DDR, like I showed you, and I will also have the system user, so you can have all of this in my GitHub under the newly created folder here, int Linux application. I hope you find this tutorial useful. Thank you and goodbye.